Okay, so we're going to begin our lecture today. We're going to continue working on from section 6.1 in TAN's calculus, antiderivatives, and the rules of integration. So another way of saying antiderivatives is also the integral. Now, last time we were talking about kind of the area under the curve. So that's kind of what we were last time. So we had some sort of, here's a graph that we have, okay, and we have some curve. We call this y equals f at x. And I should always remember, oops, to label my axes. So now what we do here is we're interested in finding an area under the curve from in a particular region. So let's say here to here. So we have a region, and it goes from usually defined from A to B. And so we actually have a mathematical notation to describe that. So that's the integral of f at x dx. So it's integrating along that curve from A to B. And from last time, we also had a couple of integrals that we could easily do. We had, if we wanted to integrate, say, x to the n dx, that was equal to 1 over n plus 1 x to the n plus 1 plus c. And this is only if n is not equal to minus 1, because then we have a special rule for that. So as an example, we'll put an example below here. So if I had like an example of x to the 3 dx, then that means that x, we increase the exponent by 1, so that it goes from 3 to 4. And that 4 also goes into a denominator, so I get 1/4 x to the 4 plus a constant. So just to make sure that when you are doing this, you can double check. You can also take the derivative of that, so that I get 1/4 x to the 4th plus c is equal to, and then we take the derivative of that. So it goes down a degree, so a third, and the third comes down, and we can't forget about this. Uh-oh, did I make a mistake? I think I did. Uh-oh. And we take the derivative, and that's 0. Okay. So what did I do wrong there? So just a second. So if I have I should be doing something like that. So it should actually 3 comes down, and then I'm left with, should just cancel, so I'm just left with that. Okay. Ooh, don't know why I made that mistake. Alright, so the next thing, we had e to the x dx. So this was another rule here. So again, if I have the integral of e to the x dx, that's just, it's itself plus a constant. And we also have, let's make sure I move the paper up. I have the integral of 1 over x dx, and we did that last time, that's equal to the ln of x plus c, and this is provided that x is not equal to 0. Okay. And we also had two properties. So there's kind of like, here's kind of a rule of integration, here's a rule of integration, here's a rule of integration, and then I'm running out of color, so we're going to go purple now. Okay, so then there's the properties of integration. So very similar to what we did with the derivative. Then if I had d by dx, I had a constant times a function, that I can move that constant in front of the derivative. And the same thing happens with the integral, that if I integrate the integral c f at x dx, again, we can move that constant in front so that I get c of the integral of f at x dx. Then the second one is very similar to like our sum one. So if I have the derivative of f at x plus g of x, that's equal to the derivative of f with respect to x plus the derivative of g with respect to x. And the same thing happens with the integral. We can actually apply the integral to each individual component. So the integral of f plus g dx is equal to the integral of f plus the integral of g. Okay, so we have all of our rules. Let's see if I can try to keep it all on the same window area. Put those pens to the side. So let's look at, here's kind of an example or a review. And I want to integrate x at 3 plus 9x squared plus 7 e to the x plus 5 over x dx. Okay. So using property 2, I can break all that up into individual integrals. So I have the integral of x cubed dx plus the integral of 9x squared dx plus, so this is by kind of, I don't know what color I used. There we go. By 2. And 7e to the x dx plus the integral of 5 over x dx. Okay. And the next thing is by, say, rule 1, I can bring out those constants in front. So there's no constant in front of here, so I can leave that alone. I can bring out the constant in front here. So I get 9, the integral of x squared dx, plus 7 times the integral of e to the x dx, plus 5 times the integral of 1 over x dx. And then we can start to apply rules. So we have rule 1 that we can apply to this one. So that is, oh, we already did it right here. So the integral of x cubed is 1/4 x to the 4th. Now don't worry about the constant yet. We just kind of tack that on at the end, so don't worry. So this was by rule number, well, we had this one right up here, which was, I'm going to call it the power rule of integration. Then we have 9. And we multiply that by, we have to integrate x squared, so that's 1/3 x cubed plus, and again that's still by the power rule. We have 7 times the derivative of e to the x, and e to the x is just e to the x, so I can leave that, e to the x plus 5. Now I can't use the power rule on 1 over x. That has a special rule, which is this one right here. And so that's ln x. So it would be 5 times 1 over, the integral of 1 over x is equal to 5 times ln x. And then I can't forget my constant of integration, so there's the plus c at the end. And I guess we could clean that up a little bit. We got 1/4 to the 4th. 9 divided by 3 is 3x cubed plus 7, and I'm just rewriting this again. Plus c. And that's all that we have to do for that question. So inside of a question like that, you know, there's 1, 2, 3, 4. There's at least 4 marks right there that could be on a final exam. I'm not saying that it's going to that exact question, but it's, you know, it tests a lot of information that we've covered in the last lecture. Okay. We've done a lot inside of section 6.1. So what I'm going to plan to do is kind of work through more problems through the section. We did a couple yesterday, some of the exercises, but I think today I'll kind of work through some of the word problems, and we'll also kind of do some of the other kind of less turn the crank. So the first one that I picked out was 51, and it says something like find f at x by solving the initial value problem. So what do they mean by initial value problem? What they mean is that it's usually some sort of derivative. And in this case, they gave us 2x plus 1, and they give us some point on the original function. Remember, when we're differentiating, those constants go to 0, and we kind of lose information as we're differentiating. So we've lost some information in this derivative. So in order to get back to the original function, we need some additional information, and that's provided in this. They're telling us that the original function at 1 is equal to 3. So, and they tell us that they want us to find f at x. So, f at x, and this means that we have to integrate, or we have to use our power rule of integration to get back to the original function. So I have 2 times x. So that is, we're going to use, well, I'll write out the 2. The exponent goes up by 1, so it goes from 1 to 2, and we also have to divide by 2. We have a constant, so you can think of that as x to the 0. Right. This goes up by 1, so I get x to the 1. And again, it's 1 over 1, so I can leave that alone. So again, most people will just write x plus a constant. So the function that I have currently is x squared plus x plus c. Now it's that constant c that we have to solve for. We have that information, so I'm going to plug that in. So plug in so I get 3 equals x squared. Oops. Because I got to plug in the 1. So it's 3 equals 1 squared plus 1 plus c. 1 squared is 1. 1 plus 1 is 2. Bring it over to the left-hand side here, and c is equal to 1. Which means that, therefore, the original function f at x was equal to x squared plus x plus 1. And if we differentiate that, we should get back the original function. So again, 2x plus 1. So again, the 2 comes down in front, it drops by 1, 2x plus 1. Okay, so that's what they wanted. So when you see something like find f of x by solving the initial value problem, this is the initial value. This is the value in the original function, and they'll tell you what it is. Okay? So you could probably do the other questions like that, 52, 53, all the way to 58. Similar questions like that. So like this. So 52 to 58. Okay. What's the next thing that we'll do? 59. 59's a bit wordy. I won't even bother writing that out. What this tells us, it says find the function f given that the slope of the tangent line to the graph of f at any point x, f at x, is f prime at x. We know that. And that the graph of the f passes through the given point. Okay, so what they're telling us is that this is the original point on the function, and this is the slope of the tangent at any point x, but that's also the derivative. And basically, with these two pieces of information, we'll be able to find the original function f, and we'll be able to solve for that constant of integration by using that additional information of that point to root 2. So, very similar to what we did with our initial value problem. I have f prime at x, and I think that's 1/2 x to the minus 1/2, and the point that they're giving us is 2 root 2. And just to make sure, so that's the original function 2 at square root of 2. Okay, so then we integrate. So I could write it just a little bit like this. I could do the integral, which means that I'm integrating this, which is equal to integrating 1/2 x to the minus 1/2 dx. And using our rules of integration, I can pull out that 1/2. And now I can integrate. So the x, this goes up by 1, so minus 1/2 plus 1 is equal to 1/2. So that's 1/2. And that goes into the denominator as well. So 1 over 1/2 like that, plus a constant. So 1 over 1/2, that is equal to, and then I can equal, for some people who might have difficulties with fractions, I could also write that as this is equal to 2 to the minus 1, which means that that's equal to 2. So I have 1/2 is equal to 2 x to the half plus a constant. And then the half multiplies by the 2, so that cancels out with each other. So boom, boom. Or this equals square root of x plus c. Now, we have to figure out what c is in this case. So, we plug in the f at 2 equals square root of 2. So I get square root of 2 is equal to, and then I have to substitute in 2 in this case, so I get square root of 2 plus c, which means that square root of 2 minus square root of 2, c, that's equal to 0, which means that our original function that we were working with is f at x square root of x plus nothing more. Okay, is there any questions about that so far? Ooh, okay. So we did that. Seemed fine. Okay, what's the next one? We'll move on to 63. So again, we just kind of look at the book. And it's the velocity of a car. The velocity of a car in feet per second t seconds after starting from rest is given by the function f of t equals 2 square root of t. The domains from t is from 0 to 30. We need to find the car's position. So I write out kind of the information that's important. Right, the velocity. That's equal to, this is what we're given, the domain from 0 to 30. And they ask us to find the car's position. Remember, this is in feet per second. So again, I have to remember my units. Find the car's position at any time. Okay. So again, that requires us to remember that when we were differentiating, we start out with a position function. Then as we differentiated the position function, we got the velocity. And then if we differentiated the velocity function, we got the acceleration. And if we integrate it, we get back to the, we can go up. So if we start with the acceleration function, we can integrate it to get the velocity. If we have the velocity, we can integrate it to get to the position, which means that our position function, s of t, is equal to the integral of v of t dt, or that's equal to the integral of 2 square root of t dt. Now I can convert that to an exponent, so that's just a half. Using my rule, I can pull out that 2, so I'm just left with t to the 1/2 dt. Now I'm going to integrate this. So again, the exponent goes up by 1, so that means that this is going to be t to the 3/2. It's constant. And then 1 over 3/2. And so 1 over 3/2 is equal to 1 over 3 times 2 to the 1. I can bring that 2 up here. So it becomes 2/3 t 3/2 plus c. And I can simplify that. 2 times 2 gives me 4 over 3 t 3/2 plus c. in the back of the book they don't have the plus C, and as I'm reading this very carefully, I don't think that they give us any more additional information. What it does is it tells us the velocity of the car after starting from rest is given by this function, the velocity function. It doesn't actually tell us what position it started from initially. So, for this question, I'm just going to say that we want to figure it out what C was. Well, we can assume that the car started at the position time equals 0 is equal to 0. So it's some origin or reference point. So in that case, we've got S of t right here. So we plug that in. 0 equals 4/3 of 0, 3/2 plus c. That equals 0. So c is equal to 0. And therefore, the position function is equal to 4/3 t to the 3/2 and plus 0. So there it is. Easy. Okay. What's the next one that we have? So the next one that we're going to work with is 65. And this is a watch company manufacturing travel clocks. And they tell us that we have some company, so it's the daily marginal cost for producing a particular clock particular model of the clock is there's 5 zeros, 1, 2, 3, 4, 5 x squared minus 0.009 x plus 8. And they tell us that this C prime, or the marginal cost, is measured in dollars per unit, and x is the number of units produced. Okay, then they also, this is one piece of information. Then they also tell us that management determined that the daily fixed cost is $120 per day. Okay, and then they say required or find the total cost incurred in producing the first 500 clocks per day. Okay, so there's kind of our 3 points, which means that What are they asking for? They want us to find c of x, and that's the total cost. Now, we talked about cost functions before. Usually we have some fixed cost plus the variable cost, and usually that is a constant. So when we take the derivative of this, the fixed cost is a constant, which means that if we take the derivative of a constant, that's 0, so that the derivative is just of the variable cost. So what I'm trying to say is that they've given you an initial value problem. They've given you the derivative. They've told you what the constant is of integration here, because that's the constant that's lost when we differentiate. And all you have to do is find the original function c of x and plug in 500. That's it. So that's kind of our plan. So find c of x, plug in x equals 500 into c of x. Okay. So when we integrate this, let me move this up. Let's see how far I can move. We need to integrate this. So the exponent goes up by 1. And I just leave this original 1 right here. 1, 2, 3, 4, 5 minus. That exponent goes up by 1, so it goes from 1 to 2, so 2, and then we divide by 2, 0.009 plus, I have 8, so that just tack on an x plus c. Okay, so we can simplify this a little bit. 9 divided by 3 is 3, so that's 3x cubed minus 9 times 2, or sorry, 9 divided by 2, that's 4.5, so that's 0.0045 x squared plus 8x plus, now what is that c? Well, the fixed cost, if we produced nothing, we produced 0 clocks, we still would have to pay 120. So that is our c. That's the 120. So again, here is the variable cost. And there is our fixed cost. And we're told that. Okay, there's our function. C of x is equal to this terrible polynomial. And they want us to plug in 500 into this. Okay, so that means 0.000003 times 500 cubed minus 0.0045, 500 squared plus 8 times 500 plus 120. Yes, these are pretty, well, they're not too rough, but I will use a calculator for this. So, I don't know if this will fit in here. Okay, so I pull up my HP, and I start out with 0.000003. Okay, I have 500. We're going to cube that times that. So this first term is 375 minus 0.0045, 500 squared. Multiply that. So this is 1,125. And I'm going to subtract that. Then the next term is 8 times 5. And that should be 4,500, or sorry, 4,000 plus 120. And so our total is $3,370. And that's it. So, therefore, the total cost of producing the first 500 clocks is $3,370. Okay, so that is what we do for 65. So besides the usual question of are we allowed to calculate on the exam? No, the numbers will be fairly decent. You won't have something where you will require to square, I don't know, 500 or to cube 500. Okay? And are there any other questions? Okay, so there's lots of other questions they could look at too. For instance, here's one like revenue functions. 66. The management of the watch company has determined that the daily marginal revenue function associated with producing and selling their travel clocks is, they have R primed is equal to minus 0.009x plus 12. And so they tell us that this is going to be the dollar per unit, and this is X is the number of units sold. So basically, it's determined the revenue function Rx associated with producing and selling it, which means that you differentiate that. And I assume that there's zero revenue if there's 0 watches sold, so there would be your kind of initial condition that you would have to figure out Rx. And then it says, what is the demand equation that relates the wholesale unit price with the quantity of travel clocks demanded? And the demand, well, you would have to actually look at you would actually have to look at what you got in terms of, you'll get something like R, and usually you'll have to probably factor it so that you would get X times P of X, and that is your demand function. So whatever you got here in R of x, you would probably need to factor it so that you had an x out in front. And then this is your demand function, and that's the price that the customers are willing to pay. And then you would have to relate that to the number of travel clocks demanded. Okay? So there's lots of cool different problems in here. There's 67 again. Canon. Okay, so it must be kind of like to avoid the actual Canon camera company talking about electronic flashes. And again, same idea. You'll probably have to. This is interesting. This is a different one. But usually something like this, 68, finding the total cost. They tell you the marginal cost. You'll have to integrate it. There's usually a fixed cost here. That's your constant of integration, and you find your C of x that way. So the question shouldn't be too difficult. They're just trying to show you how the integral or anti-differentiation is also useful in terms of business and economics applications. And of course, there's other applications as well, because this textbook is also for the social sciences and life sciences. So stuff like population growth and ozone population and surface area and flight of a rocket, deceleration, acceleration. These are kind of more for the physical sciences, or life sciences. And so I really wouldn't worry too much about questions like this. Questions we're kind of using acceleration, deceleration in terms of when I was explaining things of integration and differentiation. Remember we were talking about this, that we had the position, if we take the derivative of that, we got the velocity, and we took the derivative of that, we got acceleration, and if we integrate it back up, we can get back to the original function. So something like these, 78, 79, those are also good to practice with as well. Okay, so we've covered applications of the antiderivative. Hopefully these problems will also give you more experience in the skill of anti-differentiation, or we'll also call it integration. And if you have any questions, feel free to email me. You know what my email is. I'm not going to say it on YouTube. And also, let me do something. I don't know if I'll be able to try this. If I do window capture. Okay, let's do that. Okay, so we got integrals. I'm live streaming. We had the derivative. So if you go to my website, there's my website. You can click here. We have a new website here, so make sure to check it out. I usually will post links. There's the assignments. There's solutions for assignment 9. And I'll usually put the links here so that you can be able to watch previous videos here. So there was my last video that we did for our lecture. And we also I also have review videos that you can also check out. So in terms like, there's the power rule for derivatives. I kind of did this a couple years ago. So if you need some more practice, or you can't remember what the rules were for differentiating, they are right there. There's also some other kind of general problem type questions to help you get ready. Okay. So let's see if I get rid of that. Okay. Again, thank you very much for tuning in. If you have any questions, feel free to send me an email. And we'll meet again on YouTube on Monday at, I believe it's, well, at the usual regular time. Okay? Take care.